it's Ian Erhard.
And Zoe Lederman.
And today we are going to run through our R script and demonstrate the use of the Lagrange Multiplier method to maximize theoretical utility functions in light of scarcity. We also demonstrate the behavioral economic phenomenon of time inconsistency. That is that our character in the problems that we'll go over may make a plan today about future behavior, but when the future arrives, they'll want to do something different. And here we'd also like to give credit to Hal Varian and his textbook Workouts in Intermediate Microeconomics, a book from which we borrowed large parts of the problem that we'll go over today.
So the setup. It's early on Monday morning and our protagonist Daryl Dawdle must write a term paper. Since Daryl's instructor will not accept late papers, it is crucial for Daryl to meet the deadline. The paper is due on Monday morning, so Daryl has 3 days to work on it. He knows that it will take him 12 hours to do the research and write the paper, but Daryl hates working on papers and likes to postpone unpleasant tasks. He also knows that it is less painful to spread the work over all 3 days rather than doing it all on the last day. So, for any day t, let's denote xt as the number of hours that he spends on the paper on day t, and xt plus 1 and xt plus 2 to be the number of hours he spends on the paper the following day and the day after that. At the beginning of day t, Daryl's preferences about writing time over the next 3 days are described by the utility function u. So, if Daryl were to, for example, spend 2, 7, 3 and 3 hours working on his paper on these 3 respective days, the output of his utility function would be minus 31.5. So it's probably worth noting that this is negative because Daryl doesn't enjoy grueling tasks, and the writing his paper is particularly grueling. So here we are dealing with disutility, something that in this case we would like to minimise.
So suppose that on Monday morning, Daryl makes a plan by choosing xm, xt, and xw to maximize his utility function. That is the number of hours that he'll spend on his paper on Monday, Tuesday, and Wednesday. So he could then plug those number of hours into his utility function to figure out that utility. Daryl has also imposed a time constraint for this paper. He only wants to spend 12 hours working on it. And that is described by the following function. So when we input the number of hours into this function, it should equal 12. For example, if Daryl spent 2, 7, and 3 hours working on his paper, then this should be true. And look at that, it's true. That's good. So our question is, how many hours will Daryl plan to work on Monday, Tuesday, and on Wednesday? Daryl's gonna solve this problem using the Lagrange multiplier method. We create the Lagrangian function L in the following way. And we can rewrite this equivalently as such, which is going to make it easier for us to take partial derivatives. Oh, where are we?
Sorry about that.
Okay, so here's our Lagrangian function. Now we take the partial derivatives of L with respect to each of the variables. xm, xt, xw, and lambda are Lagrange multiplier. And they are described in these derivatives are described in the following ways. And now we set these partial derivatives equal to 0 and construct a matrix to represent the resultant system of linear equations. So So here's our system of linear equations, and matrix multiplying this matrix by a column vector of the three variables and the Lagrange multiplier, we get the following column vector. So now we construct an augmented matrix by binding our matrix mat with our column vals and get the following. Here we're going to use the package Pragma. So if you don't have this and you're following along with your R script, then you would uncomment this download packages command. And now we are going to solve the system of linear equations with ref and use to get the reduced row echelon form of our system. The variables of the last column represent the number of hours that our protagonist needs to spend on his paper on Monday, Tuesday, and Wednesday, respectively from bottom to top. So on Monday, Daryl will spend 2 hours on his paper. On Tuesday, he'll spend, looks like 4 hours on his paper. And on Wednesday, he'll spend 6 hours on his paper. And then entry 4, 5 in the fourth row, fifth column is the solution for the Lagrange multiplier, which just helped us solve this problem. So suppose that Daryl doesn't want to waste so much precious time crunching these numbers every single time he has a paper due, but he still does want to maximize his utility, or in this case, minimize his disutility for working on the paper. So Daryl decides to write an R script for himself to do this, of course. And we describe this, and he creates the following function. With the argument hours to complete, he just needs to enter the number of hours that he wants to spend on his paper, and this function will spit out, using the same method that we just used, the number of hours that he needs to work on his paper in the next 3 days in order to maximize his utility. Now, say Daryl, here's an example. So for example, if Daryl needed 30 hours to complete his paper, he ought to allocate his time as follows, thus minimizing this utility. So on day 1, he would spend 5 hours working on his paper, day 2, 10 hours, and on day 3, 15 hours. Boy, doesn't that seem like a lot of work. So now let's assume that we can generalize Daryl's utility function for working on his paper at day I from the first day of work as follows. That means that we could also make a more general function to let Daryl, using the Lagrange multiplier method, minimize his disutility for any number of days that he has to work on his paper and any number of hours that he needs to complete the paper. This function is also going to spit out a graph, a plot, indicating the number of hours that he needs to work on the paper each day. So, for example, say Daryl has a paper that he has 7 days to complete, and whose completion will take 20 hours. Then he can enter the arguments 7 and 20 into this function, and he gets the following output. So Daryl will need to spend about 0.7 hours on day 1, 1.4 hours on day 2, 2.14 hours the next day, then 2.85, 3.57, and 4.29, and 5. And you see that in the graph on the right-hand side of the screen. And clearly, it's a linear relationship.
Okay, so now in this part we'll have a look at what happens on Tuesday. So as we saw earlier, if Daryl has a time constraint of 12 hours on Monday, Daryl will then spend 2 hours working on his term paper. So it's now Monday morning, and Daryl gets up and he knows that he has 10 hours of work left to do. So before deciding how much work he can do on Tuesday, Daryl will naturally consult his utility function. So this tells him that on Tuesday he will spend 3 1/3 hours working on the term paper, and on the Wednesday he will spend 6 2/3 hours working on the term paper. But on Monday we saw that Daryl planned to spend 4 hours on Tuesday and 6 hours on Monday to complete his term paper. So we can say that Daryl doesn't have time-consistent preferences. But this seems a bit odd, so let's look at this graphically to see if we're correct. So we're going to use the package numDeriv to look at this, and if you don't have it, install it using the code that we've commented out. So let's first plot the indifference curve that our utility function specifies. So an indifference curve is a graph showing the combination of two goods that give the consumer equal satisfaction and utility. First, let's construct our indifference curve. So as Daryl cannot work on Thursday, his utility function now looks like this. And so that's exactly the same as the first one that we showed, but without Thursday. And let's rewrite this so R can plot the contour lines using vectors as follows. And now let's plot the indifference curves. So we also know that Daryl's time constraint is the total number of hours that Daryl is willing to spend on the project. And so let's plot a number of these options on our graph. Great. So we know that Daryl is actually only willing to spend 10 more hours on the project, and we want to maximise his indifference curve subject to this time constraint. So as you can see, this is the time constraint that we want to maximise it to, and we're looking for an indifference curve that is tangent to this line. So reassuringly, it does look like that it is probably that the point which is tangent to the line is probably close to 3.3 and 6.6. So let's zoom in to confirm. Okay, so there's a lot of red lines there, but we can read an approximate solution off the graph. So at point 3.333 recurring and point 6.666, we can see that we have a tangent. We have a tangent at this point to the constraint 10, and we have approximately confirmed our solution. So in this example, we can see that Daryl's choices are not time consistent. Of course, there might be another more self-aware procrastinator who may factor this behaviour into their decision-making process. But Daryl Jordal looks forever to put off his work and leave it to the last minute. We hope you have enjoyed Daryl's conundrum.